This video will be discussing the program code used for the PizzaBox prototype. First thing, we include the libraries that are going to be needed for the program code. First is the Wi-Fi library for the Wi-Fi connections, as we are using an Arduino Uno Wi-Fi Rev 2 board. The next is the library for controlling the M6E Nano module. This is the simultaneous RFID tag reader from SparkFun. This library is provided by them. And the next is a vector library for storage handling. This stores the data that's read in from the RFID board and is used then to pass that data on to the Apache server, the local Apache server. As well as that, then we have libraries for the LCD display and the definitions for the connections. The connections usually over the A0 to A2 pins on a normal Arduino Uno, the non-Wi-Fi version. With the Wi-Fi version, due to architecture changes within the main chip, it's connected over the CSL and SCL and SDA pins on the Arduino Uno Wi-Fi. Next definitions then are for Wi-Fi connectivity. We use the secret underscore SSID and the secret underscore pass. This is so we can include a header file which has the Wi-Fi details in there that these variables are defined in that header. This helps to maintain privacy when dealing with Wi-Fi credentials. And then we instantiate an instance of Wi-Fi client. Next definition then is the server. This is the address for the Apache server. I run mine on a local client, so depending on your connection, this will change. Next is setting up the variables used for the data that's passed into the post request. These will be used further on when sending the data to the Apache server. Next one is for the supporting routines. This is mainly used if the SparkFun module is unresponsive, and you can just, instead of resetting the Arduino, you can send any character over the serial port and it will try and restart the SparkFun RFID reader. It's useful for debugging and if there's any failures with wiring or power problems. Next definitions then are for the amount of EPCs. So the EPC is the unique identifier for the Gen 2 RFID tag. For the prototype that I use, the maximum could easily be set at about 10, as that's more than enough ingredients, but to be safe we set it to 20. So each ingredient has its own RFID tag, each tag has its own unique EPC, so it could be a maximum of 20 unique identifiers being read by the RFID board. EPCs have a max byte size of 12, so lowering this will cut off any data. Increasing this will just add zeros to the end. HTML buffer as well, the size of the buffer that's sent then to the server. Here we're constructing the EPC vector, allocating the space and creating the vector. Next is the RFID shield definitions. So this included including the header file for the software serial. This is so we can transmit to the device. And the software serial, this is the pins in which the the pins in which are used to connect the RFID shield to the Arduino. For the RFID shield to connect, be able to communicate, then we set the serial speed to 38,400. This is a standard. This code can be seen in the example libraries that come from SparkFun, as well as defining the region. Valid options are, as seen, this project was developed in Europe, so set to Europe. Setting the amount of power, the SparkFun RFID board has a variable power draw for increased range. So if you want it to be able to read tags up to 16 foot, then you can set the power to max. You can also use an antenna. An antenna is something that was not used during this project, but you can use that also. The power is set to max in this code, as the RFID reader needs to be able to read through a certain amount of plastic to be able to give stable reads of the RFID tags through the plastic. We set it to the max possible. So this is just for debugging. The next definition here, so for the program debug, setting this variable to either of these options gives different outputs over the serial port while the program is running. Obviously useful for debugging, seeing where the program is going wrong. The next one is just a variable to control how long we actually scan for tags. This could be altered. We set to 30 seconds as through testing. That gives us more than enough time to be able to scan for all the tags that are on the pizza base. Next definition is just for the button pin. So this changes depending on where you've connected your button pin. Obviously, buttons majority would have two pin inputs, one to ground and wherever there is a pin free. So you define here, and then create an instance of the nano, which is the RFID shield. Next definition then is for the serial port. This defines the baud rate for the communication over the serial port. For the next part, we're going to talk about the two main loops within the Arduino. In the setup, we simply begin the serial port over the baud rate that's been defined previously. Next, then we set up the LCD's number of rows and columns. The Adafruit LCD screen that we're using has 2 rows and 16 columns. And we set the backlight to high to be able to give the user most visibility when looking at the LCD screen. We then simply print out to the LCD screen, initializing. This gives the user then information that the prototype is initializing itself, and then once it's finished initializing, we set the cursors back to row and column 0, and then we print out the please order. At this point, then the prototype's ready to be used, and the program is initialized correctly. The setup uses 3 main functions that will be discussed later. Connect Wi-Fi is just to initialize a Wi-Fi connection. The init RFID function initializes the RFID shield, and then the array underscore init initializes the array to be able to collect the data and then send it to the Apache server. The second main loop, then the loop. First, we reset the cursor of the LCD display to row 0 and column 0. This is so we're able to print out to the LCD screen new messages. Once we've pressed the button, once the button pin is then low, it outputs to the serial port that an order's been placed, as well as printing to the LCD that an order's been placed. Printed to the serial port to the serial port just allows you to follow through the program over the serial port as well as on the display on the prototype. So for the next while loop, we simply scan for tags using the defined amount of time. During this time, we run the check EPC function. This function will be discussed further on, but it essentially just checks for all the functions. The EPCs, all the tags that are on the pizza base. While this is also running, we set the cursor back to 00 and 01, and then we output to the LCD screen that we're checking for ingredients. This is to give the user then more information on what the program's doing. Once this is finished, we print to the serial port then that it's finished checking for tags, and then we run two functions that send the data collected from the RFID shield to the server, as well as clearing the array after the data has been sent, ready for the next user to make an order. Otherwise, while the button hasn't been pressed, continuously waiting for button to be pressed will be output to the serial port. So we can keep track of where the program is over the serial port, and the LCD will reset then the cursor to 00, and it will just print out please order, so the user knows that the prototype is then ready for the next order. The next part of the program code we'll look at is the connection to the Wi-Fi function that was defined in the setup loop. So first off, most of this code comes from the example sketches that are provided with the Wi-Fi Nina library. Simply, first if statement is just checking that the Wi-Fi module is available and if the Arduino board can communicate with the module. If it can, it continues through the code, checks the firmware version. This is calling a function from the library. If the firmware is lower than the set amount, then it'll recommend to upgrade the firmware version, and it won't go any further. Next while loop then just outputs to the serial port that is attempted to connect to the SSID that you've defined in the Arduino _secrets header file, and then it will try to connect to that, then delay in 10 seconds. After 10 seconds, if it's connected to the network, it will print out you're connected to the network over the serial port, and then we'll run this function. This function simply just prints out the SSID of the network and the IP address, signal strength, to give you a bit more information about the network you're connected to. The next functions we'll look at are the RFID routines. This routine is called in the setup loop of the two main Arduino loops. The first thing it does is try to connect to the RFID reader, and this is outputted to the serial port. If the RFID module fails to respond, if there's a wiring issue, powering issue, etc., it will output to the serial port that it's unable to respond, and using a function that is defined further down, this allows us to, instead of resetting the whole of the Arduino board, allows us to simply input a character into the serial port, and then it will retry connecting and initializing the RFID board. If it is connected fine and it's able to communicate with the RFID shield, the program will continue setting up region protocols. If you're using an antenna, it will call these functions from the library. RFID region and RFID power are previously defined at the start of the code. We've defined ours as Europe and 2700. This allows for the max dBm to give us a more consistent reading through the plastic base. It then starts the reading then calls this function, starts the reading. So whenever we call our function to start checking for tags, it's able to scan for those tags, and then it prints out to the C report that it's been initialized correctly. The next part depends on what variable you've given the program debug. If you've given it a number greater than 3 or 3, it will enable the debug mode, which is a function in the SparkFun library. And then what you'll get then is, if the module is continuously reading, it will not asking it to stop. If you get a wrong opcode response, if it is all good, if it is all good and it can communicate with the RFID shield, it'll try and reset the RFID speed. So this is what we defined earlier at the start of the code, and it will try and restart it, reset the speed to be able to reattempt that communication. The next bunch of functions we'll look at are to do with the array routines. First off, the array initialization is called in the setup loop of the Arduino. So this is one of the first things the program does during the startup. And all it does is to initialize the array to be able to capture the detected EPCs from the tags that are scanned. The data that's scanned from the RFID board. So this sets the size of the vector using the space that we've defined previously. The array count function simply counts the number of entries within that vector, the amount that we've scanned and read. The clear one simply clears the array. We use this once we're finished sending our data and we need to reset the array for the next user. The next function then adds this EPC that we have scanned to the vector only if it's not already in there. So what we do is go through each of the entries in that vector. We check each entry for a match. If it's not found, then we'll add that then to the vector. If it is found and our variable is set for the debug to be greater than 1, it will output to the C report that is found in the array entry, and then it will return at what point in the array it is, and then continue scanning. If it is then, again, we've got our program debug variable greater than 1, it will output to the C report that it's not found, and it's then adding it to the vector. The next part is a sort of sanity check that there is space available in that vector to be able to add more. If it's full, it will just print out to the C report that we cannot add any more. This you can avoid by setting the space definition that we discussed earlier to a greater size, but this is useful for debugging purposes. So the last bit then is just adding that new entry into the array. So we just do the EPCs.pushback, which appends the new EPC to the end of the vector. The check EPC function that is called in the main loop of the Arduino is used primarily to start checking for the EPCs of the unique EPCs of each tag that comes into contact with the RFID shield. So first, what this function does is it returns the response type, and it calls this function from the library. And what this does is when this function is called, well, if we look at the library here, the example response that you get from this is this sort of array of hex values. And what this does is to break down this array of hex values into a tag ID, RSSI, frequency, and the timestamp. So if it's able to make that response, if it's able to get that information, then it'll keep it alive and continue scanning. If a tag is found, so if the RFID board picks up a tag, it'll extract that EPC from that tag. So this array of data will be retrieved from that tag, and to be able to extract the EPC, it will look in the certain index into that array to retrieve that EPC, which is here. So this is the EPC ID. This is the information that's getting returned. This is obviously different depending on what you've written to the EPC, but this is the information that we need to retrieve from the tag. So this is the information that's been taken out of that array. It will then get that information and add it to the array of all the tags that we're going to be scanning, and then that's then used later on when we need to take those EPC entries, convert them to strings to be able to post. Again, for debug purposes, depending on what you define the variable at the start, we can also retrieve some more information, the RSSI, frequency that the tag was detected at, and the time that it was read. All this information can be extracted from the array that we are able to extract from the tag. So that these are useful for debug purposes, and we're also able to print it out in bytes then. So we're able to see in the serial port what exactly the EPC is. The next function to be discussed is the post data routines. The post data function essentially makes a HTTP connection over port 80 to the server and posts the data. Post data function combines the data caller header with the data recorded from the Arduino and the RFID shield. Arduino data is a string, and it packages them into the data that is sent in the post request. So the first thing that the post data function does is call this vector2string, essentially removing each EPC from a vector and converting them into just one string. So it goes through the vector, removes each EPC, and then adds a comma between each EPC, and then returns Arduino data. We add a comma in between each EPC because later on, when I discuss the PHP script we use that then to be able to separate each EPC. That Arduino data is then sent to the post data function. It is combined with the data column in the variable data. Then connects then to the server, the IP address that you've defined previously, and over the port 80. Prints out to the serial that is connecting. If it's able to make the connection, then it will send the data, send the post request, and then continue on in the loop, in the main loop. If it's unable to make the connection, it will output to the serial that the connection failed and is disconnected. Then it will stop the client. The next bit of program code we're going to look at is the PHP script that we use to be able to convert the hex data that's retrieved from the EPC of each tag, convert it to ASCII, and then format it into something that's readable by a user, and then send it over email to a defined email address. So first off, once we retrieve the data that's sent to the client, first off, we define a function that's used to turn hex values into ASCII, and this function is used further on in the PHP script. So once we retrieved that data, first off, we replace all the blank space in the data. We remove that blank space. Next, what we do, we look through the string, and where it's separated by a comma, we add it to an array, and then converts a string separated by commas into an array of individual values that are separated by commas. We then get the max size of that array exploded, and we use this then to be able to loop through the array and then call in the hex to string function at each index within that array. So at each index of the array, we take the hex ASCII, and then we convert it. The hex values, then we convert it to ASCII. We then use this implode function to convert the array back into a string and separate each EPC with a comma. What we found also is that when we're not filling the EPC, as the EPC is a maximum of 12 bytes, when we're not filling that EPC with what we've written to the EPC, for example, if we've written onion, we still get leftover bytes. Those leftover bytes come out as zeros. So to make it more readable, we will just remove the zeros from that string. Next, then we set the variables ready to send over the email. So the recipient, the subject line of that email, and the message that we want to send, as well as the headers. We then use those variables that we've defined previously here to send to the mail server that's hosted on the XAMPP local server.